All right, so the goal for this video is to approximate the area between f of x equals 5x minus x squared and the x-axis. What we're going to do is use four rectangles of equal width because we really don't have a way to find the exact area yet. We don't know how to deal with parabolic shapes. So there's three methods we're going to look at, and that's finding the left-hand endpoints, using the left-hand endpoints, using the right-hand endpoints, and then using the midpoints. And then we'll compare and contrast the different methods to see which one gives us the closest. So, or at least what we can tell is the closest anyway. So using left-hand endpoints, so what we're saying is we first break the interval 1 to 3, which is our interval right here. And we're going to break it into four equal pieces called subintervals. So the first notation bit that we have to talk about is this idea of the width of each rectangle, which we call delta x, and that is computed by finding the difference between the endpoints of the interval and dividing by the number of intervals. So here, n is equal to 4, and this is the interval a to b. So here, the width of each rectangle is going to be 1/2. So for left-hand endpoints, we take each interval and we take the leftmost point on the interval to determine the height of the rectangle. So that means on the interval 1 to 1.5, it's going to be there. And we're just going to label the left-hand point of each interval. So here, the rectangles are going to look like this. And as you notice, all but one of them is an underestimate, meaning that it's not quite as high as the graph. So meaning taking the area of the rectangles is going to leave us with a lower value. So what is the area? Well, the area of the first rectangle is 1/2 because that is the width of the rectangle. And the other one is the y value when x is 1. So I'm just going to write 1/2 f of 1. What's the next one? 1/2 times f of 1.5. Then the next one is 1/2 times f of 2. And then 1/2 times f of 2.5. Now you might notice we can make this a lot more simpler by factoring out a 1/2. So we have this. And so getting all those y values, now I have these off to the side here, so I'm just going to write them down. When we plug in 1, we get 4. When we plug in 1.5, we get 5.25. When we plug in 2, we get 6. When we plug in 2.5, we get 6.25. So if we add those together, well, let's see. That's 1/2 times, so that's 11.5 plus 10 is 21.5. So it looks like 10.25 is our left-hand endpoint estimate. Okay, so there's left-hand endpoints. Now let's go to right-hand endpoints. We're going to do the same thing. Most of the stuff carries over, except that now we're using right-hand endpoints, which means on each interval, I'm now using the rightmost point in the interval to determine the height of the rectangle. And now you notice, for the most part, except for this last one, that last one has issues. It just doesn't conform to the others. It must be in its own little world. We notice that the rectangles mostly go over the curve, which means it's circumscribing the curve, which means it's going to give us a larger area than the actual area, but at least the concept is the same. So the area is 1/2 f of, well, let's see, that first y value is the y value at 1.5 plus 1/2 f of 2 plus 1/2 f of 2.5 plus 1/2 f of 3. Okay, now we already have most of these values before, but I'm going to just go ahead and factor out the 1/2 anyway, just to make this easier. And now let's see, 1.5 was, okay, so it's 5.25. This was 6. This was, I believe, 6.25. And f of 3 would be 6. I don't know why I put a comma there, but that that this ended up there. Boy, now we're just really having issues here. There we go. And now that means this is 1/2 times, well, let's see. 5.25 plus 6.25 is 11.5, plus 12 is 23.5, which looks like 11.75. Now, one other estimate, now knowing that the left-hand endpoints is probably lower than the actual area, and the right-hand endpoints is likely higher than the actual area, one other thing we can do is take the average. So I call this L plus R over 2, and let's see what that gives us. We have 10.25 plus 11.75 all over 2. Well, that looks like 22 over 2, so the average of those estimates is just 11. Interesting that we got such a nice number there. So that's probably our best guess for the area or the area under the curve at this point anyway. So let's just take a look at one more, and that means midpoints. Now, midpoints you might think is the same as what we just did with the 11, but not quite. With midpoints, what we're doing is taking the midpoint of every subinterval and using that to determine the height of the rectangle. So that means I'm going to draw my rectangles this way. So there's my 4 rectangles, and then mathematically, what is happening here? Well, it's 1/2 f of, now, what is this value right here between 1 and 1.5? It is 1.25. And then what is the next one? Well, it should be 0.5 away, so that should be 1.75, and it is, halfway between 1.5 and 2. So you have 1/2 f of 2.25, and 1/2 f of 2.75, and then naturally I'm going to factor out the 1/2. I just write all the rest of these down, and I have these off to the side, so just plugging in 1.25, 1.75, etc., etc. So 1.25 gives us 4.6875. 1.75 gives us 5.6875. F of 2.25 gives us 6.1875. And F of 2.75 gives us, again, 6.1875. So if we add those together, we get 1/2 of, let's see, 4.6875 plus 5.6875 plus 2 times the last one, since it showed up twice. 1.87. Okay, so this is 22.75, and this turns out to be 11.375, so a little bit closer, okay, at least presumably. So the question now is, what is the actual area and which one is closest? Well, let's see. I'm going to do this off to the side here because I don't want to give away the secret yet, because there is more calculus coming. So we have, do that, hocus pocus and all that other stuff. And it looks like the actual area is 11 1/3. So that 11.375 is really, really close. So just to summarize, the notation that we use is that area, at least by the approximate rectangles, is approximately equal to the sum of the function at certain values times delta x, where we're subscripting the value. So what this means is f of x1 plus, whoops, I forgot the delta x. F of x1 times delta x, now that is the area of the first rectangle, right? Delta x times the y value, plus another delta x times the y value, all the way up to the last value of x that we're plugging in, and there's always n of them. If we have n rectangles, that means we have n things to add up. And of course, that means we have delta x times this sum right here. So it's just basically adding up a bunch of function values, whether using left, right, or midpoint, or some other weird algorithm, you can do that, okay? So that's what's going to give us the area of the region, or at least an approximation. So the big question is, how do I make this approximation better? The main thing we can do, since it's in our control, is we can use more rectangles. What you probably notice is if I were to squeeze 8 rectangles in there, we'd be able to get closer to the curve and we wouldn't have as much of that extra gap space there. So using more rectangles will definitely help out with this. But of course, in terms of doing this by hand, you don't want to do more than 4, 6, or 8. So at least we're going to keep this doable for now. So I thank you for watching, and I hope this helps areas with rectangles make more sense. Thanks again.